Hello, this is Michael Lee from Dixie State University. This is just going to be a presentation of my computer science final project of the spring 2014 semester. So I'd just like to quickly review what my project is, what I did, and talk about how my predicted expectations and tasks compare to my results. So let's just review what I did for my project. So the concept is to use an accelerometer that can be worn on the wrist like in a bracelet by an athlete, and to be able to send the data from that through a means like Bluetooth to a mobile device to calculate the speed of a pitch or a throw or a swing or whatever it is the athlete is doing. So the main part of the project was to prove this concept, to see if it's feasible, if it works, if it's possible. And a lot of my dream and hope tasks for this project was to actually make an app that could do that and to be able to send it via Bluetooth. So since my project is quite physics heavy, I'd like to review kind of the physics that went into the calculation of this. So in this picture here is just some of my notes, but it's what I based my calculations on. Thanks to the help of some professors at the university like Curtis Larson from the computer science department and Sam Tobler from the physics department, we were able to work our way through this. So using linear equations for movement, in this equation that you see here, you have your final velocity is equal to your initial velocity plus acceleration times time. So there's a couple problems with this. For one, the acceleration of a pitch or a swing is not constant. It's changing throughout the entire duration, and so in order to get a better, a more accurate result, we need to use the fundamental theorem of calculus. So let's review that really quick. So the fundamental theorem of calculus basically states that here we have this curve and we want to have the area under the curve. And so what we do is we break it into these little sections, these little rectangles, and we just add them all together. So as you can see here in this picture, this is one rectangle, and so you find the area of this rectangle and then you just add it to all the areas of the other rectangle. And the smaller width sides of these rectangles is the more accurate and closer to the actual area you'll get. And so that is what that is using here. So what we want to do is to get the summation of all these rectangles. So for our first calculation, for my purposes, we had to start from rest. So we can assume that this initial velocity is 0. And what we're going to do is we're going to add the acceleration that we're reading at that moment times our time frame. And you can think of this delta t as the width of these rectangles. And that means for my second iteration, so if my first iteration was a rectangle here, the one right next to it, instead of starting at initial velocity of 0, its initial velocity is the result of the rectangle that came before it. And so as you can see, we have the velocity of I minus 1 plus its current acceleration times the same time interval. Since I'm having all these rectangles the same width, I'm taking the same sampling rate. So using that and also linear algebra, we're able to use these calculations to try to get that area under the curve, which is the velocity. So let's talk about vectors for a second. Since we're dealing in 3 dimensions, we have 3 vectors. We have an x, y, and z. And what we want is the result of all of them. So in this picture, you can see that we have this x, y, and z, and together they make this one vector A, which is in solid black. And so Using the Pythagorean Theorem, we can think of this as the square root of x squared plus y squared plus z squared, and all that is in the square root bracket. And so let's look at how it's used. So hopefully this works. Here I'm just using a Google Hangout to show what I'm doing on my Windows machine, since I was having problems recording that screen. So here is my code. I'm using an Arduino Uno chip that I programmed, and it's connected to a VirtualBotics 3-axis accelerometer. And so basically what it's doing is, in this loop, I have it at every 200 milliseconds or 0.2 seconds, it's going to take a sampling rate. And it's just going to spit out an X, Y, and Z. And I have it configured, so instead of just spitting out in its default g-forces, I have it spitting it out in meters per second squared, so I can do the physics a little easier. So let's do an example. So here I have my code. I have my chip hooked up to this computer, so I'm just going to open this serial monitor, and this window pops up. It's going to calibrate itself, and now it's just starting to spit out these numbers. As you can see, the x and y vectors are hovering around 0, maybe a little above, a little below, but around 0, and that's what's to be expected. I just have my device laying here on my desk, and so it shouldn't be moving at all. But in the z direction, it's reading around a negative 9.9 or sometimes up to 10, and the reason for that is gravity is acting upon it. So if we think of gravity as a 9.8 here on the Earth, then that makes sense because it's hovering around 9.8. Sometimes it's jumping a little above, a little below, but that's where it's staying. And so we're getting these readings, and we just need to throw it all together. So let's stop that. And to do my calculations, before I wanted to write an app to do all of it for me, I wanted to prove the concept first. So to do that, I made these spreadsheets where in this column, just throw in the raw data that I got from that serial monitor that I just showed, and I just break it into the 3 separate vectors. So what I measured for my x, y, and z's. And here is where I do all my calculations. So for the very first instance, that first rectangle you could think of, we're just assuming we started at rest, and for my testing purposes, that's what I tried to do. So you can think of this as 0 times, or 0 plus the acceleration at that moment times my time sampling rate. And since in my code down here I had it set for 200 milliseconds or 0.2 seconds, that's what my delta t is for all my calculations. And as expected for each calculation after the first one, I use my previous velocity. So that's what that is right here. And I'll explain why I'm using this average thing in a little bit. But basically, I calculate these velocity vectors for each axis, my x, y, and z, and I get this result vector here. And so I made a little graph to show its results, and here it is. And I guess I can explain a little about this test. What I did, I just had it start, and then I picked it up, and I started waving around a little, and I put it back down. But according to this graph, it says that I was waving my arm around, or faster than 150 miles per hour. That's pretty fast. And let's talk about why I'm getting these skewed results. So back to vectors. I want this vector to be the result of all 3 vectors, But what's happening is, if you look at this picture here, if my movement is this vector A, in each instance that I was reading, I was getting an instance for gravity. Gravity is a constant. And so what's happening is, instead of getting this direction here, it's pulling my direction down towards gravity. And since gravity is constant, it thinks it's accelerating at this constant rate. And so for each iteration, it thinks it's going this direction. And that is why my graph is accelerating. It thinks it's going faster and faster. It's because of that gravity. And so that was a main problem that I ran into. I spent most of my time trying to work with this gravity problem because I don't want to know how fast I'm going with gravity. I want just my movement alone. And so, doing some research, I discovered that using other hardware such as a gyroscope, you could keep the orientation of your device, and that way you'd know which way gravity is towards, and you'd be able to filter that out of your calculations. But before I went and settled on buying more hardware for the project, I decided to do some control testing. So what I did was, I had my brother drive me around in his car. We tried to drive her in fairly flat places, starting from rest, so we'd have to stop a lot and just take a lot of data samples there. I'd use the speedometer to gauge how fast I should be going, and throwing those into the spreadsheets to get a calculation. And since we were going around flat areas and I kept my device on the floor of the car trying to keep it flat, just trying to get basically only my X and Y axes. And let's look at some reports about my testing results. At first, I wasn't converting my things properly. I was comparing miles per hour to meters per second because that's what my device was measuring, and then I forgot to convert to miles per hour. But even then, I was averaging about a 20% error margin. So let's talk about other means that I went through to try to get a more accurate reading. So if you remember back in this spreadsheet, in my calculations for my velocities, I'm using this average thing. So since we're dealing with physical measurements in the physical world, we're not getting completely accurate things. Like sometimes it's going to think it's a little faster, slower, and get these spikes in our measurements. And that is called noise. And so to try to filter out that noise, I'm taking this average. So for any given spot, I'm using the average of the previous 5 to try to filter out if one of those was one of these spikes or like a big dip or something. Hopefully that would smooth it out so I could get a better result. And so doing that, we get a graph that's more like this, and that's a lot more reasonable. That's about 34 miles per hour. Maybe I can wave my arm around like that, but it's a lot more reasonable than like what this is saying, 160. So that seemed to help out a lot. But even then, coming back to my error report, with noise and trying to filter out that gravity, I was still hovering around this 20% error. And so I had to do some more research on how I could improve this. One article that I found really helpful was this one by CH Robotics, and they basically talk about how just answering a lot of questions, is using an accelerometer a good way to estimate position and velocity. And I like the answer that they share here. And they say the short answer is yes and no. They talk about how these low-cost sensors are very poor in quality, and they say it's simply unusable for such a thing. They talk about how gravity is a problem, and how even if we had a gyroscope to keep the orientation, That's a hardware thing as well, and so there's going to be errors there. And when we think about it, back with the fundamental theorem of calculus, if you look at this example here with this rectangle, it has this area that is not part of the curve. And so each rectangle is not completely accurate. And so we have this snowball effect where we have these inaccuracies adding together. And I did, however, have one test where we were driving about 30 miles per hour and I calculated we were going 30.6. So that was the closest result I ever got. I was unable to replicate that. As you can see from these other results, this one we were going 35 and my calculation says we were going almost 50. So in summary, compared to what I thought I'd accomplish at the beginning, I didn't get nearly as far. And that is because I had to change my focus. Instead of focusing on developing a whole app and something that's all working, I decided to focus more on what my client wanted, and that was to prove the concept. Is this worth pursuing, making an actual app? And in short, I'd say, is it possible? Theoretically, yes. We have all the moving parts, we have things. If everything worked properly, we could do it. But that's the problem, everything's not working right. We have hardware that's getting noise and getting things that aren't accurate. The whole nature of the calculus is there's always going to be an error margin there, but having a 20% error margin, I don't think it'd be beneficial for a pitcher who can pitch, let's say, a 100-mile-per-hour ball, but they're getting readings anywhere from 80 to 120. So hopefully in the future, as hardware and technology improves, that won't be a problem, and this would be a feasible and accurate means of calculating the speed for athletes. But until such a time, I'll have to say that the error is too great for any real use and purpose for this. So thank you for watching, and hopefully you found this interesting. Once again, this is Michael Lee from Dixie State University.